So the due date is week from this Thursday, so March 24th, and there are only two problems. So I hope it doesn't take long to do. Today, I noticed this afternoon that we have a seminar starting at 5 o'clock. The speaker is Professor Kim Yong-hwan from Seoul National University. He is going to talk about sea keeping programs that he has been working on. So what I'm suggesting to do is I'm going to give you a lecture of 30 minutes from now to 5, and then all of us move to the seminar room, and then he's going to talk about wave-body interaction problems, which we will study later. Okay, so that should be good. The introduction to what you're going to learn. Although the depth of the material might be a little too much at this point, but you can get an idea what kind of problems we are going to look at later. Okay, so that's what I'm going to do today. If I knew that the seminar is scheduled today, I could move today's makeup class to some other time, but it's too late anyway. So probably also you don't want to hear my lecture too long today because you have been you have suffered from my lecture this morning. So probably 30 minutes is long enough for you. But the attending the seminar is mandatory, so please attend the seminar. Okay. All right. So we found a solution for a circular cylinder, and today, now we are going to do is to find the general solution of the Laplace equation. Of the Laplace equation in 2D. So we solve Laplace equation in polar coordinates. So as I wrote earlier, this is Laplace equation written in polar coordinate. And last time we used this method of separation of variables, and so at that time we wrote velocity potential as a function of r times function of theta, right? And for circular cylinder problem, we assume the h theta depends on h theta is nothing but cosine theta, okay? But that's the true for circular cylinder. But for general problem, it doesn't have to be true. So we leave h theta as unknown at this point. And then what we do is we substitute this expression into here, and then we'll get the following. So when I take a second derivative of phi with respect to r, we'll get this, right? And then I'm taking first r derivative. So we wrote in separable form, and when I take a r derivative, nothing happens to h. Okay, so this is a method of separation of variables. Right, and then when I take this second derivative with respect to theta, I'll get r squared r times h double prime equal to 0. So prime means the taking derivative with respect to r and h, So at this time we divide, the equation by RH. So divide by RH, and then we end up with R double prime, and then and multiply by R squared. So I have multiplied by R squared and divided by RH, and H. I have a H in both numerator and denominator, so they will go away, and then I end up with 1 over R, R prime, R plus, and then I have H double prime, H equal to 0. Okay. So first I multiply by R squared, and then divided by R times H, and then I end up with this. And then this is a function of R. So these two terms depend only on R, and this term depends on theta only, and therefore for this plus this to be 0, the only possible choice is, this has to be constant, and this has to be the same constant with a negative sign. Okay, because this depends on only theta, and this depends on R. Okay, so we are saying that is some constant, let's say C, and then H double prime H has to be minus C. Okay. And this time, I don't know what the C is, but when I look at this guy, and H is a function of theta, so H function has to be 2 pi periodic, because, theta changes from 0 to 2 pi. So whenever you go back to the original, position, which is, which means, theta changes from 0 to 2 pi, you hit the, exactly the same point. So it has to be 2 pi periodic, and meaning that this constant has to be, integer. So for example, cosine m pi or sine m pi will be, n theta will be 2 pi periodic if n is, the integer. If n is not integer, then this doesn't have to be, 2 pi periodic. Okay. And why I'm looking at cosine and sine? Because, if I put C equal to minus n squared, then I end up with H double prime plus n squared H equal to 0. Okay? And then H has to be either cosine n theta or sine n theta. Okay? Or linear combination of those. So once again, from here to here, this is what we have. But in this case, H would be cosine square root of C theta and sine square root of C theta. If C is positive, that's what we assume. If C is not positive, if C is negative, then you have exponential function, which is not 2 pi periodic. Okay? So C has to be positive. That's the first thing. And also for 2 pi periodic, this has to be, integer. Okay. So that's why we put, n squared instead of, c. And then we found, the function h. And now we know what the c is. So we write the equation for capital R as minus n squared R equal to 0. Okay, so I replace c by n squared. And then I move this guy to the left-hand side after I multiply by capital R. And we know how to solve this. We assume R is R to the mth power. And then m minus 1 plus m minus n squared is equal to 0. So I'm taking the second derivative, which will give m times m minus 1. And then I have r m to the minus 2. But I have a 2 here, so I end up with r to the m. And likewise, I have r to the m here. But they are all the same, so I drop that. So that's the equation for m. And then this guy goes away. And we end up with which means m has to be plus minus n. So here n is integers. So here, let me put number 1. Let's say n, c, the case when c is n squared, which is not equal to 0. Okay? And then what we have is an r to the n plus bn divided by r to the n. So m has to be plus n or minus n. And then linear combination of those can be written in this way. And then I have to multiply cosine n theta. Likewise, I have a cn Rn plus dn divided by Rn and sine n theta. So that's the general solution when c is equal to n squared, which is not equal to 0. Okay, this is the most general solution for this case. And here, I don't know what a sub n, b sub n, and c sub n, d sub n are at this point. I have to impose boundary conditions, and on the body surface and infinity, then I will find a sub n, b sub n, c sub n, and d sub n. And n is the integer, so I have to take summation from 1 to infinity. Okay. So here integer with a positive integer. It doesn't matter, if you put a negative, this becomes a positive power. So I don't have to include the negative part. Okay. So the reason why I can write this is r is nothing but r to the n or 1 over r. So I took the linear combination of those, and that's what we have. So the second case, C has to be constant. And here we said, C has to be positive. That's why I put in n squared. What if C is 0? Okay. I exclude that. And then what we end up with is H double prime H is equal to 0. And which means H is what? A naught theta plus B naught, right? Or let me write this way, because I have to take a linear combination. Either theta or 1. So if you if you integrate once, you'll get a constant. And then if you integrate one more time, you'll get a theta, okay? So those are the general solution for this guy. And for R, you end up with this, right? So when C equal to 0, and this time we can solve this in the following way. I divide equation by R prime and then R squared. Then I end up with 1 over R equal to 0. No. I still can solve the way that we did. Sorry. So we get m minus 1 plus m equal to 0. So this means m is m squared is equal to 0. So we substitute here r equal to r to the m. And then we end up with this from the first term, and from the second term we get this. Okay. This might not be a general solution then. So and then this gives the constant, right? Okay, so in this way, I will end up with A0 theta plus B naught. I need a log R. Is there any other case that I have to consider? Okay, let's check whether this is the most general case or not. So for example, I can do what I did before. I integrate once, and then I will end up with, right, plus constant. So don't write it. let me just check. So R prime has to be 1 over R times C1. Okay, so this is not the most general one. And then I get R prime is C1 log R plus C2. Okay. So the method that I took here gives only one of the solutions. The other solution is log R. So to get that, what I need is divide by both sides by R prime and R squared. Then I end up with this. So this is exactly the same as that. And then I integrate once with respect to R. Then I will get log R. And then log R prime. And then this will give minus log R plus integration constant. And then this one will give you this. This is exactly this. And then I integrate one more time. And then I'll get this. Okay? So let me correct this. So this method gives you the only one solution because it gives double root. So this is not the most general way. Sorry, most general way is doing this. So R is given by 1 and log R. Okay? And then we have to combine these two to get how do I write this? Okay. A naught plus B naught plus C naught log R plus D naught theta. Okay. So let me call phi 1 and phi 2. And the most general solution is so this one I call phi 1. So most general solution phi is phi 1 plus phi 2. Okay? So that plus this. So this general solution can represent flow around a body of arbitrary geometry. Okay. The problem is we don't know what A sub n, B sub n, C sub n, and D sub n. We have to find them by imposing boundary conditions. But find determination of those constants is not straightforward. It's not easy, except for simple geometry. For example, the circular cylinder, we know what we need now. Okay. So if you have flow like this, then we need only cosine theta, so which means n equal to 1. That's what all we need. And then we have A1R plus B1 divided by R cosine theta. And we don't need any, term proportional to sine theta, so this guy will go away. Okay, so we need only one term from here, one term from here. And this guy, so let me write that down. So for a circular cylinder, we have phi, which is A1 R cosine theta plus B1 R divided by R times sine theta. That's it. We don't need, the phi 2, any of those. So what is this? This was R cosine theta is a X. So this is a uniform stream. And this is a perturbation that we wrote capital phi. And at that time, B1 was found U times A squared. Okay. So for a circular cylinder, you need only two terms among infinite number of terms here and here. Okay. But if you have a, the cylinder whose cross section is not, circle, then you need an infinite number of terms. Okay. And in general, you cannot determine all infinite number of terms, so you make a truncation. So you just took, a finite number of terms and impose, boundary conditions, approximately to find, the coefficients of these, these series. Okay, but in general, if you use the infinite number of terms, then you can represent any flow around, a cylinder of arbitrary cross section. So we'll talk about that a little bit more, okay, on Thursday, and it's 5 o'clock. So we'll move to the seminar room, and let's hear what Professor Kim is going to speak about. Okay.